All right, so the topic of today's lecture is thresholding. If I can get my window to open here. Come on. Why do you suck? All right. Here we go. Okay, so the topic of today's lecture is thresholding. And so the basic idea here is that last week we were talking about edges, mostly, edges and lines, right? So we talked about how to detect kind of individual edge pixels. Then we talked about how to connect up those edges into objects, and specifically the problem of using the Huff transform to find long straight lines in the image. And today what we want to talk about is kind of the first road to what you'd call image segmentation, which is basically if I have a foreground object and a background, the question is, how can I separate the foreground from the background, right? So as a general problem, this is called image segmentation. And this is a topic of lots of computer vision research in terms of how do I best separate stuff in the foreground or objects from stuff in the background or the scene, right? And so the easiest way to start with that problem from a very low-level pixel processing point of view is called thresholding. So the easiest method is the following. To say, okay, I'm going to assume, for the purposes of this lecture, that the stuff I'm interested in is either brighter than the background or darker than the background, okay? And so what I could say is I'm going to make a binary map that is 1 if the image pixel intensity is greater than some value, and 0 if that pixel intensity is less than some value, right? And the idea is that in theory, this should be the object, and this should be the background. Okay. And so let's just show a simple example of that. So here I have a sculpture that I took a picture of. So here, this is like a, kind of hard to see, but basically this is a view of Venice through this sculpture. The letters in front of me are dark, and the Venice behind me is bright, right? So actually in this case it's kind of flipped around, right? The stuff that suppose I'm interested in is the dark letters, and I want to throw away the background, right? So in this case, since the letters are all virtually black and the background is blown out to be bright, it should be pretty easy to do something very simple. So for example, what I could do is I could say my foreground is the regions of the image that are less than, let's use some value, right? So 20, for example. Right? So if I use that threshold, that looks okay. And actually I can see here that there are some little artifacts, right? So for example, there's a bright region, kind of a brightish region in the middle of this O or theta, or whatever it is, that didn't get picked up by the threshold. And then there's another bright thing here that comes from like a reflection on this letter that's off to the side that didn't get fully picked up. But for the most part, I did pretty well. And I could play with the threshold to see if I could get a better segmentation. So for example, I could say something like, what if I tried to use a threshold that was a little bit more conservative, like a threshold of 10. Here I can see that I didn't pick up maybe everything that I wanted, right? So I've got regions of the image that are not picked up, like probably because the edges of these sharp lines are probably a little bit higher pixel intensity than 10, and so along these edges things get fuzzed out a little bit. And on the other hand, if I was to be more liberal and say, okay, show me all the stuff that's less than 50, then I would get actually more white pixels, right? And in this case, I got a good number of white pixels. Pretty much everything inside the letters, I guess, is okay. like I picked up this part of the theta that I missed before, but now there's some dark stuff in the background that's also starting to get picked up by the threshold, right? And so it's not a perfect science, and I'm trying to fool around with trying to find the best threshold. So one thing that might guide me, for example, is looking at the histogram of the image. So here I could see, for example, that the dark pixels that are on the left are the ones that I really want to find, and all the stuff on the right corresponds to the stuff that's showing through the letters, right? And so kind of the name of the game today is, how can we choose the best threshold, or at least an a priori good threshold for an image without having to manually screw around with it, right? Is there an automatic way to choose this threshold? That's what we're going to talk about for most of the day. And so kind of conceptually what I want to do is I want to find a dividing line in this histogram such that everything below the line is foreground or background, everything above the line is foreground, right? So basically foreground on one side, background on the other side. And it's never going to be perfect, right? So the thing we're going to talk about on Thursday is, for example, once I've got this foreground, maybe there are some holes that I missed in the foreground. How can I automatically fill those holes in, right? So we're going to talk on Thursday about so-called morphological image processing operations, which are good for cleaning up holes and little extra pieces that I don't want in the image, working with binary images. So that's kind of a fun lecture, but we won't get to that until a few days. Okay. So like I said, the key question is, basically I have the histogram of the image, and so this is basically intensity, and this is the probability that the image equals the intensity. And I have some distributions. This here is kind of like the best case scenario where there's a clear hump for the foreground or background, here's a hump for the other one, and I want to draw a dividing line, and this number t is my threshold, right? And so the key question is how to choose this t. The easiest way, obviously, is to try and choose a t that works for the entire image, right? Which is easy to implement, but sometimes may not give us a good result. The alternate approach is to choose a local threshold, where basically, say around every pixel, I have a pixel-specific threshold that tells me what should be foreground, right? We're going to talk about that a little bit later in the lecture, okay? So basically, we have kind of a choice between a global threshold for all pixels versus what I would call a local or an adaptive or a pixel-dependent threshold. So we're going to talk about both of those things today. Okay, and so generally the kind of quality of how well an algorithm works is going to depend a lot on what this histogram looks like and what the characteristics of the image are, right? So there are a lot of factors that may affect the performance of this kind of object segmentation algorithm. So if there's kind of very low contrast between the object and the background, so say the object doesn't stand out very much from the background, that's going to be a harder problem. If there's noise in the image, for example, Gaussian noise, that may corrupt, it may flip some of the pixels that should be foreground to background and vice versa. If the object that I want to segment is very small with respect to the background, it may be hard to pick it out, even though it may be bright. For example, it kind of might get thrown away by an algorithm like, suppose we were to try and median and filter the image, the objects that we care about, like stars in the image in the presence of salt and pepper noise, may be hard to find. There could be variability in illumination. I'm going to just do an example of that in just a second, where basically if the kind of illumination of the image, say there's like a gentle, gradient coming in from the window, or maybe even a sharp edge of light coming in through the edge of a window, it could be that can really throw a global threshold out of whack. So let me just show kind of an example. Let's see if I can put this together. So here I'm going to make an image just of a circle on a background, if I can remember how to type. And so if we haven't used this before, this mesh grid is basically a function that makes arrays corresponding to a square array of points on the xy plane limits that I specify. Okay, so here I've got limits from x going minus 50, 50, y going minus 50, 50. And so now I'm going to make an image that is going to be a binary image, and I'm going to ask for all the points where the radius is less than, so let's say this is a 100 wide image, so let's say that the radius is less than 20, for example. Right? So here's my image. Now, clearly, if I were to look at the histogram of this image, it's just going to be black and white, right? Because I don't have any other colors. It's just like a bar graph where most of it is black, most of it is, the other half of it is white, right? Nothing very interesting, and so that's a really easy thresholding problem. Now, instead, maybe to make it a little more interesting, let me make, instead of making it 1 as the brightest value, I'm going to make a gray value of 0.75. So now if I look at the histogram of this image, I've got some stuff on black and some stuff on kind of light gray. Okay. So now what I want to do is add some noise to this image. Okay. So I can use the imNoise command to noise up this image, and I'm going to add. I forget how this imNoise works. So. So I'm going to add some Gaussian noise to this image. With 0 mean and variance, say, 0.02. Now, if I look at the histogram of the image, it's going to have values spread across the entire grayscale axis, right? And that's because there's now a probability of getting non-zero and non-0.75. And if I look at the image, I should see that, it's kind of probably hard to tell. Oops. So here's the original image, and here's the noisy one. So, you can see that now the background has some light pixels in it, the foreground has some dark pixels in it, okay? And so, again, if I wanted to try to threshold the sky and say, only show me the foreground pixels, well, let's look at my histogram for a second. I could still try to draw the line, let's see if I can make this a little bit. I could still try to draw the line maybe say above 0.5, let's say. So if I were to look at all those pixels greater than 0.5, and then I were to look at the original image, all the pixels greater than 0.5. Right? So the original image is on the right, this new threshold is on the left. I can see that number one, I've got some pixels inside the circle that were basically too dark, right? They got pushed down into the background region. And I've got some pixels in the background that are too light. They get pushed up in the foreground region. And so, I've kind of got this case where it's hard to know what to do, right? Because if I were to make the threshold lower, right, that would mean that probably I would pick up these guys in the middle, so we can try doing that. So if I were to, say, make the threshold, lower, now I've got most of the circle, but now I'm picking up more brighter pixels in the background, right? So I have to do something about those, right? So there's no way to get the exact segmentation anymore. And of course, if I were to make the image a little bit noisier even, so if I were to make a noisier image that had even a higher variance, so now let's try taking that image and thresholding. First of all, let's look at the histogram of that image. whoops, that didn't work. Well, first of all, the image is on the left. So now you can see that the shape of that circle has really been corrupted by all this noise I added to it, right? And if I were to look at the histogram of it, now things are rough because it almost looks like the image histogram is uniform, right? It almost looks like I've histogram equalized this image, right? And so now any threshold that I choose is inevitably going to have some, background and some foreground. So if I, again, try to threshold it like this, I'm going to get something, oops. I'm going to get something like this, where now, oops, I somehow lost it. I have this little side-by-side function that I wrote, and I always need to have two figures, otherwise it won't work, right? So here, basically, again, now my problems are worse, right? Now, let me just say that all is not lost, and we're going to talk about how to fix these kinds of problems next time. But all I'm trying to get at here is that the thresholding process is tricky because of noise. So that's one reason. Another reason things can be tricky is because of kind of gradient. So instead of adding noise to the image, let's instead add kind of like a spatial gradient to the image. So for example, let's say that I take a gradient that is like from, so I'm going to take a vector of ones like this. I'm going to multiply it by a vector that goes from, say, minus 0.8 to plus 0.8 and in 101 steps. So this is basically a gradient that goes from dark to light, right? And if I add this to my image, now I have something that is basically going a circle that goes from dark to light. And if I were to try and threshold this guy, so say I was going to try and threshold this thing to be, again, I know that the true color of the inside circle used to be 0.75. So if I threshold at 0.7, life should be okay. But if I were to do that, suddenly I have a problem, right? Because the stuff on the left-hand side of the circle is no longer that bright. And conversely, if I tried to pick that stuff up, I would start to say, okay, well, maybe my 0.7 threshold is now too high. What if I tried to make like this, greater than 0.5? Now I get more of the circle, but I also get more of the right-hand illumination that is just like there from extra illumination, right? So here, this is an argument for, I need to have some sort of a local algorithm that says, for example, if I'm locally brighter than my neighbors, then color me 1, otherwise color me 0, right? So global threshold is not going to cut it for this problem, okay? All right, so we're going to talk about some of these issues in just a second. But first, I want to talk about kind of this idea of basic global thresholding. So, under the assumption that things can be pretty well separated, how would we do that, okay? So let's start talking about that, sorry. So global thresholding. So let's assume we use the same threshold for everything. What is the best way to choose that t? What is a good criteria? So how to find the best threshold, okay? And so, I think that we need to define what we mean by best, right? And I think the easiest way to do that is an algorithm called Otsu's algorithm, okay? So basically a classical method for doing this is called Otsu's algorithm. Okay, and so what is the idea? The idea is to say, okay, we're going to try to split the pixels in the image into two classes, okay? foreground class and background class. And the idea is that I want to choose a threshold that makes those classes as well separated as possible. So within each class, I should have the variance of the distribution be as low as I can, and I also want those two means to be far apart from each other, right? So the idea is that I want to maximize this so-called between class variance. Another way to say this is a good threshold should separate the pixels into clusters that are as tight as possible. Okay, and so for this, we're going to use a little bit of probability. Okay, so all of you guys should have probability. And so what I'm going to do is first I'm going to look at the statistics of the pixels across the whole image. And then I'm going to say, okay, suppose that I chose a threshold. Now I'm going to have some conditional probabilities. The probability, well, the mean and the variance given that I'm in a certain class. Okay, so we're going to have the image histogram, or, you know, let's call it like the image probability mass function, right? So here I'm going to define little pi equals the probability that my image pixel is equal to this intensity. And I'm going to assume that I ranges from, you know, 0 to however many levels in the image I have. So L could be 255, for example. Okay, and now I'm going to have the global mean of the image, right? That's defined just as the definition of the mean for a PMF, right? I take the intensity and I multiply that times the probability of that intensity. So this is the global mean. And then I have a global variance, which is defined as the expected value of my squared distance away from the mean, right? Right, so by itself, the global variance kind of tells me how spread apart is the histogram of this image, right? Worst case is uniform, best case is, you know, delta function, right? Okay, so this is kind of like the global statistics. And now what I'm going to do is, you know, suppose we select a threshold t. What we're going to do now is compute the class conditional mean and variance for that threshold, okay? So how does that work? So that means I'm going to take this threshold, okay? So I'm going to have a set of pixels, which is basically those pixels that are below the threshold. And I'm going to have another set of pixels that are above the threshold. And I'm going to have probability 1, which is basically the probability that I'm in the first class, which I know I should be able to get just by adding up, you know, the first k probabilities. And the probability that I'm in the other class is the remainder of that, right? By the way I set this up, you know, these two things have to add up to 1, right? So now I have two classes. And I can compute the class conditional mean and variance, right? This is like saying, given that I'm in class 1, what is the mean and the variance of those pixels? And that's easy to compute, right? So basically I can say that, you know, actually I don't think I need the variances. I guess I just need the means. Well, I guess I can say them both. So this guy, the mean in class 1, is just the conditional mean over the probability of being in class 1. And this guy is similarly this guy. Okay. And so we're going to use these two class conditional means to define this criterion that we're going to try to make as good as possible, right? So Otsu says, so Otsu's criterion is to maximize the between class variance. So that's defined as this thing, sigma b squared. So it's like saying the probability of being class 1 times this guy plus the probability of being class 2 times this guy. So it's kind of like saying, you know, I want to look at how far apart the two means are from the center. And so maybe the way to think about this is that I've got two, you know, pixel distributions, and I'm drawing a threshold. So let's say I draw this here. That means that these guys are all in class 1, these guys are all in class 2. This is my conditional mean for class 1. This is my conditional mean for class 2. My conditional mean, or my overall mean for the whole thing is probably going to be kind of skewed over here. And what I'm trying to do is I'm trying to basically place this threshold so that these two guys are as far apart as I can make them, and also far apart from the global guy, right? Because what this is saying is basically I want to look at the sum of squares of this distance squared plus this distance squared weighted by how many pixels there are in each class, right? So if I do this right, I'm going to get two clusters that are as far apart from each other as possible, and the global mean is hopefully going to be somewhere in the middle of them, far away from both, right? That's the kind of philosophy. Okay. And then if I wanted to say that, you know, so this is basically hopefully a number that I am going to make really big, right? And in some sense, what I want to do is I want to look at the ratio. So let me say the ratio of this between class variance over the overall variance is a good measure of separability, how well these classes can be really separated. So higher is better, you know, more separable. Separability. Okay. So we could talk about, you know, how would I optimize this function. In practice, you know, since we're only looking at 256 grade levels, usually I can just do a loop over those 256 values and find me the number that maximizes that measure. So in practice, you know, we just consider all possible thresholds and choose my final threshold, t, as the k that maximizes sigma b squared. Okay, so there are some more implementation details of how this works under the hood, and you can read about that in the textbook. But this is basically the way it works, right? I have a function, and it's easy to say, okay, for a given threshold, I compute these, you know, class means, and I compute this function for every possible threshold. And so there is a function built into Matlab that does this. So called gray thresh. And so here you can see it says the gray thresh function uses Otsu's method, right? I wrote my own little wrapper around this that basically I started from gray thresh and I made some little changes to myself to plot some things, basically. So instead of just giving you numbers, I added some stuff to plot it out. So let's see. I have some images. So let's start with sunset. Okay, so So here's an example where kind of what I'd like to do is segment out this nice sharp silhouette of this background, right? And again, this hopefully is not going to be a problem that's too hard to find a good threshold for. And if I did this correctly, so I'm just going to apply my Otsu command, which is basically just a wrapper around the gray thresh command. Okay, so here I generate a bunch of pictures, right? So this guy here is the original. Then I looked at the histogram of the image, and you can see the red line is where I decided automatically to put my threshold, and you can see that that does not a bad job of, on the right-hand side, I've kind of got this nice cluster of stuff. On the left-hand side, there's like a nice local dip where the histogram goes down. And what I'm showing in this picture is, this is the plot of the Otsu error, or the Otsu cost function, right? So basically, as a function of possible threshold on the bottom, it plots the sigma b squared on the y-axis. And so the red circle is showing me where I had the maximum value, and that's where I drew my threshold. And the result of doing that is this picture here. Now again, this is not perfect, right? So if I can see this versus this, and so if I do, like this, I can see that actually the threshold does a pretty good job, except in this side of the dome, right, where here these pixels are just a little bit too, too light, right? Or maybe, yes, too light because they're falling into the foreground side. And so again, this is the point where I say, well, okay, so what did you give me, Otsu? I don't remember. So Otsu told me that my threshold should be, 0.29. And so I guess that's basically on a scale of 0 to 1, right? So that's saying that my actual threshold is 74 pixels, okay? So if I wanted to try and get that darker region, then maybe I have to do a little bit better, and I'd have to try to say, okay, I want to show me the stuff that is maybe less than 100, right? So again, I didn't really, solve all my problems. Right, so here, this is what I did if I tried to use 100. So now I've got, actually the edges of the building that I want, but unfortunately now all this stuff here, which you can kind of see comes from the fact that there's this kind of vignetting, which means that the image is darker on the left than on the right, and those pixels now are a little bit dark enough that they've gotten picked up as shadow, right? So again, this is a place where adaptive thresholding, which we're going to talk about in a second, could help me out. But we see that Otsu does a pretty good job in general. And so let's see another example. So here is a graph of the history of the toilet. Okay, so basically you can't read this. You can read it on the thing. So basically, here this is like this is almost like, wasn't a neon sign, but it's kind of like a backlit thing. So it's already almost binary, right? And actually, I think this should work really well for Otsu, right? So if I were to say Otsu of M, okay, so here the threshold does a pretty good job of picking out all this bright stuff, right? So if I compare, actually there's not that much change, right? So the left-hand image is a grayscale image, the right-hand image is a binary image, and I've kind of done a pretty good job. So for example, if I wanted to do like text recognition, for example, this might be the first step to that, right? Because I've isolated the light letters, and now I know where to find letters, right? So this might be not a bad first step, right? And there's not that much to complain about. There are a couple places in this image where, again, there's like this kind of a gradient here that goes from white to gray, and the similar thing across here. And at some point, that gradient is going to get broken by whatever threshold I chose to do, right? But it looks pretty good. And if I compare if I look at the histograms of these images, right, here it's clear that there is this great separation, right? So Otsu is trying to put that threshold kind of right in the middle of these two peaks, right? A little bit more on this side because there are more pixels on this side, right? So that's what's going to be better from the perspective of the cost function. And I can see that, again, in some sense, there's a wide range of thresholds that are probably going to do a pretty equivalent job, right? Because the top of this function here is kind of flat. So no matter which threshold I choose in this kind of range between, say, 50 and 150, I'm going to do a pretty good job. Okay. One more example. Oops. Okay, so here's another example where, again, I have dark text on a light background. I've got this light shining through these windows. And so kind of what I expect to see is kind of like some sort of, well, let's see what we see instead of talking about it. So here's another case where I have this issue with kind of vignetting, right? So there's kind of a darker area around the periphery of the image, and the image has kind of got like a more of a spotlight in the middle. So I can see that my, lighter pixels are all getting picked up here, but, I don't get, like, for example, the whole wall. So this is okay, but I mean, we're going to talk in a second about how I can maybe make a better result like this. But again, this kind of stands to reason that darker stuff gets segmented into one thing, lighter stuff gets segmented into something else, right? And so, for example, if my objective was to, for example, count the number of windows in this image, this might be a good start, because I could say, okay, now I'm just going to kind of look for the connected components of black pixels in the middle of the image, and for every one of those, I count a window, right? Those kinds of things would be like the natural next steps from this. Okay, so comments or questions about these examples? Yes?
For the histogram, when you put the threshold,
yeah.
So the left side goes to 0 and the right side goes to 1. Is that just what it basically does?
In this case, yes. Everything to the left is going to 0, everything to the right is going to 1.
Okay.
I mean, that's kind of arbitrary, right? Because, sometimes, so basically this is just like saying white is one class, black is the other class.
So just basically the threshold splits the set into the two classes.
That's right. Yeah. Like what?
With images with 3 peaks, can you use 2 thresholds or?
Right. So what would happen if I had 3 peaks? And so, yes, you can do that. So I'm just going to write that down. In general, we can extend this to finding k minus 1 thresholds to separate k classes. In that case, kind of what I'm trying to, I would have a kind of a new cost function that looks something like this, right? So I'd say, sum over all the thresholds, the probability of being in that class times the deviation from the mean, right? So I could make a more general, kind of a more general Otsu thing, right? The implementation of that would be a little bit trickier because now I can't just loop through all the thresholds once. I have to kind of find these.
Loop through them once, and then what will you have to do multiple times?
Yeah, I mean, I wouldn't, you have to do it kind of holistically, right? So for example, you wouldn't say, okay, first I'm going to find threshold number 1, then I'm going to find something else that splits one of the classes. You would probably try and find these 2 thresholds at the same time. So you kind of want to use something more like a numerical optimization to find those. Yeah, but it can be done. That's a good question. Okay, so we saw that this generally kind of works okay. And, it's true, though, that Otsu can fail when, for example, there are no strong peaks in the histogram. Right? So, for example, nothing is going to help us that much. Remember the case where I took the circle and I added that gradient to it, right? When I looked at the histogram, it was almost flat. And so there wasn't really that much that I was going to be able to do with that because there's no great place to draw that line. Or if the object is small with respect to the background, right? So suppose that I had a histogram that was like, very dark and then like some tiny peak where this is the foreground and this is the background, right? Otsu may not do a good job of finding a line between these two things because the mass of the probability is all kind of in the background. So, remedies that you can try. So one is to low pass filter, then apply Otsu. So part of it may be that, suppose I added noise to the image and that was causing my histogram to get kind of out of whack, right? Whereas if I were to low pass filter that noisy image, I would try and bring it back to something where the peaks, where the foreground was maybe more smooth in the middle and the background was more smooth in the background, and that might give me a better chance of doing a good segmentation. So that's something you can try. The other thing is to only consider pixels near edges when computing the threshold. So what I mean there is that, in some sense, what defines the separation between foreground and background? Well, you expect that there are going to be some sort of an edge around the pixels, right? Or an edge around the object. And so instead of using all the image's pixels, many of which are nowhere near the stuff I want to actually segment, instead what you could do is you could say, okay, first I'm going to, I'm going to take my image, I'm going to have my object here. So suppose that I found, pixels around the edges of the image, maybe not all perfect, but I got a bunch of pixels around the edges of the object that I ultimately want to consider. Then what I could do is I could say, okay, I'm going to draw a little boundary around my edge pixels, kind of interior and exterior to those pixels. And now I'm only going to consider these pixels here when I compute my Otsu threshold. The idea being that those guys are really the only ones that make the big difference, right? So I only care about stuff that is close to the edges I've already found, right? So this may or may not work, but the idea is that, I don't use everything, I just use the stuff that's close to the edge pixels, right? So that's definitely not built into the Otsu, Matlab function. You'd have to implement that yourself. But it shouldn't be that hard to do. Okay, so the main thing, though, that will get us around some problems is what I would call, adaptive or variable thresholding. Okay, so, variable thresholding. So the idea there is, suppose I've got this image, and again, here's the object that I want to segment. What I could do is, if there was a gradient, across this image, kind of like that circle that I drew earlier, well, one thing that I could try would be to say, okay, instead of applying the threshold to the whole image, the simplest thing I could do would be to say, okay, I'm going to split this image into, a bunch of blocks, okay? And I'm going to apply a special threshold, say the Otsu threshold, just per block, okay? And then the idea would be that if there was, generally darker pixels over here and generally lighter pixels over there, then maybe I would do a pretty good job of, dealing with that issue. And so, luckily, you don't actually have to go very far to make this work yourself in Matlab. So there's a function called blockproc, which I believe we already maybe talked about in an earlier homework, right? So the idea here is that, this applies specified function to each, and I specify how big I want the blocks to be to each block of an image. Okay. So basically, here, I wrote a little function again. This is basically, again, the gray thresh command with some stuff I wrapped around it. In fact, I guess you might be able to just use straight out gray thresh. So all I'm doing here is I am returning the thresholded block at the end. So once I found my Otsu level, I am spitting back the thresholded block according to that Otsu threshold. Okay, so an image comes in and an image comes out. A binary image comes out. And the way I use blockproc to make this happen is maybe I have to remind myself. So I specify the image, which is A, the block size, which is mn, and the function, which is the thing I want to apply to every block of the image. And so here, what I can do is I can say blockproc, and I'm still using my Windows example, and let's use, say, 100 by 100 blocks. And I'm going to call this Otsu thresh. I need to put this little @ sign in front of it. That says this is the name of a function that, or Otsu block. This is the name of a function that we're going to call at every block. Okay. So for one thing, I have this little subfunction spitting out the threshold at every block. And so here you can see that this Otsu block is choosing a different threshold for every 100 by 100 block. And if I show, so let me also figure out what was my original threshold for this image. So if I just were to apply Otsu here, I would have used a threshold of 99 for the whole image, right? Now I'm using a variable threshold across the whole thing. And so if I were to, in one side, show the image greater than 99, right? So that's going to be my original result. And then I'm going to show my adaptive version. So here, I can see that I've done maybe a little bit of a better job, right? So for one thing, let's look at, for example, the numbers, right? The numbers in the image. So here, it used to be that underneath these windows, right, it used to be that all of that text, that black text on a what appeared to be darker gray background, all of that got thrown into the background class before because the background was too shady and it didn't stand out. So now this is like saying that, hey, you know, these numbers are locally darker than their background, and now I can start to read the dates perhaps under all these windows. On the other hand, though, not everything is great. So here I can definitely see I picked up more stuff, and I've picked up more of the overall background as white, which is what I want. On the other hand, you know, the problem with this block processing stuff is that I have artifacts, right? So I can see that there are edges of blocks that come out because I'm making an independent decision at every block about what I'm doing, and so that can result in seeing the edges of the blocks when you apply this block by block thing. So I can try and play around with the blocks being bigger or smaller. So for example, let's suppose I chose smaller blocks. In that case, now I'm going to get like lots of variable thresholds. And if I were to look at this now, you know, now actually I've done a better job. And part of this, you know, is just because of the size of this image being a little bit too big for my screen. If I were to zoom in, you would see I'm actually doing a pretty decent job of finding, you know, the characters, right? So now, actually, I could say now I have some hope of automatically, for example, counting the number of windows and maybe even using something like text recognition to figure out the dates underneath the windows, right? I still see some block artifacts. And so, for example, here, I can see my 20 by 20 blocks, right? And part of the reason for that is that the image is basically constant intensity inside some of these blocks. If my blocks are too small, then I could get an entirely flat region, right? And what that would mean is that Otsu would have a threshold. Otsu would have to deal with a histogram that was basically like a delta function, and it might make a decision such that all those pixels are either, you know, flipped to one side or flipped to the other side. So in that case, you know, I'm going to get some regions like this where, you know, even though there's really nothing foregroundy about it, just by virtue of being inside this flat region, I get some artifacts. But for the most part, you know, things look pretty good. And so, again, you'd want to kind of play around with the block size to see what you got. All right, so questions or comments about this? I didn't try it on the sunset one, but let's see how we would do on that. I don't exactly know what to expect here, but oh, not good. So why was that so bad? Let's see if we make these blocks a little bit bigger, maybe. Oh, I think I probably know why this is bad. No, still pretty bad. I think part of the problem is that this image has lots of flat regions. Yeah, see, this is pretty cruddy, right? So here, I don't even know what to make sense of this image. It's so bad. Maybe if I made the block size a little bit smaller. I don't know why this would make a difference. Here I'm going to have some problems with the constant regions, though. And I probably shouldn't have done that. Okay. Nope, looks like crap. So basically, the lesson is that you can't just throw the same tool at every problem. You have to think about what was going to make sense for my image, right? The reason that the Windows image made a lot of sense was that there was a lot of detail scattered across the whole image, and by choosing blocks, I could kind of isolate that detail where I wanted it. Whereas this sunset image, just to remind you what that looked like, right? The sunset image is actually a fairly low detail image, right? It's kind of constant across this whole region. So if I draw a block that is somewhere in the middle of this thing, it's going to kind of make an arbitrary choice about what should be above the threshold, what should be below the threshold, right? So I would expect that things would probably go wrong around the sky. But then again, I would expect that if I had implemented, which I didn't, this idea of just looking around the edges of the image, right? So if I was to look at the edges of the image, and said, okay, now make me just a little bit of a dilation around each of these edges and only use those for Otsu, then I think it would probably work better. But unfortunately, I don't have that code up here right now, so I can't show it to you. Question?
With the blocks, is it possible to see like what the adjacent blocks are, and then make a decision on whether it's light or dark from there?
Right. So you could do a lot better than what I did, which is basically to say, okay, don't make a hard decision about this block until I see how it's going to affect my neighbor, right? So one argument you could say is don't do anything that's going to introduce these blocking artifacts, which I should be able to tell by looking at the boundaries of the blocks, right? So that's definitely true. Another way to get around this would be to avoid the blocks entirely, right? So let's just say that works okay in cases, but choosing block size is tricky, and you're inevitably going to get some sort of blocking artifacts. So the last thing I want to talk about is how can we avoid the blocks altogether, okay? And this is something I'm going to ask you to try on your homework. So a better thing is to adapt the threshold on a per pixel basis, not just a per block basis. And so the idea would be, okay, so let's say I have my image, and I've got my object, and I'm going to take my pixel, and at every x comma y, I'm going to build a little neighborhood around my pixel, okay? And so at every pixel, let's build a neighborhood. Let's call it SXY. And then I'm going to compute the mean and the variance of the pixels in that neighborhood. Okay? And then I can design what the book calls predicates, which is basically a fancy way of saying I have a decision rule that applies to every block. And so then we could make a rule like the following. So I could say, okay, give me all the pixels, turn the pixels to 1 if my image is greater than the mean plus 2 standard deviations, right? That's like saying, find me stuff that is locally bright inside the block, right? I need to be at least twice 2 standard deviations away from the mean, right? So that's going to isolate certain pixels just in that, so basically, at this pixel, the way to think about this is it's saying, I'm going to turn this pixel on if I am locally brighter than my neighborhood, right? And I'm making that choice at every pixel, okay? Or I could say something like, I could say, lots of possibilities. So say I could just ask for just being greater than the mean, right? So that would find, that would be kind of like a less stringent threshold, right? Instead of having to be super bright compared to the mean, I have to be just greater than the mean. Or I could say that I want to be, different than the mean by at least 2 standard deviations, right? So instead of having to be exactly brighter or darker, I instead just have to be different than the mean, right? I have to be an outlier. Or I could say, okay, I want the image to be, greater than the mean, and I also want that pixel to be in absolute value greater than some threshold, right? So here this is like saying there's a local criterion that says I want to be locally bright, and there's also a global criterion that says you need to be at least this bright to pass, right? So this is, in this way, if I have like a locally dark region of the image, so there are always going to be some pixels that are a little bit brighter than their neighbors, right? But I don't want all those pixels to get picked up in my segmentation map. I want to just say, you need to be at least this tall to ride the ride, right? And on top of that, you need to be brighter than your neighbors. And so you can kind of, play around with these things to see what works well for your image, right? Okay. So, like I said, I believe that one of the homework problems is comparing global thresholds to local thresholds in this way, right? So I think the 6th problem is exactly like this. And so again, all you have to do is kind of loop through your pixels, make a little window, compute the mean and variance, and then apply one of these predicates, okay? Okay, so last thing I want to mention is that it's true that we can also do this in the world of color, right? So certainly for the past several weeks, I've kind of talked about black and white stuff, but everything that I've said so far kind of applies to color images, and so we can also apply thresholding to RGB color images, right? So we could do this in various ways, right? So, I can threshold independently on, the RGB or intensity channels, right? So I could say I want to be brighter than this in red, brighter than this in blue, brighter than that in green, something like that, right? So that's certainly easy to combine those kinds of binary images, or, combine the channels. For example, I could compute the norm, right, between this vector, which is an RGB pixel now, and some color, right? I could compute, for example, the sum of squared distances of these 2 vectors, and then I could say, I want that to be less than some value, right? That would be like saying, okay, I want you to be within 10 pixels of this color, okay? So I made a little bit of Matlab function to do that, which is really simple, and called it color thresh. So all this does basically is shows me an image, gives the user the opportunity to pick a point on the image, and then finds, all the pixels that are within a certain range, okay? So really simple. So for once, I'm not going to RGB to gray my image. Right, so here's an image that has lots of different colors in it, right? And so now what I'm going to do is I'm going to apply my color thresh to this image. And so now I've got a little mouse pointer that says, okay, click on something. Let me make this a little bit bigger. So let's suppose that I want to click on the blue of this ribbon. What happened? I guess it's thinking. Okay. So what happened here? I don't think it's what I wanted to happen. Oh, I see. So my original plan for this function, which didn't work very well, was to take the, so my original plan was to take this number here and apply the Otsu threshold to it, right? So now I've basically got, after I do this, I've got a distance function that's a scalar, right? And I can say, okay, I expect that all the stuff that's close to 0 is what I want to segment, otherwise I want to segment the other stuff. And so here, I later decided that was pretty dumb, and it didn't work very well. So what I want to do instead is to say, okay, find me all the pixels that are within 10 units in color space, for example, of, let's say 30 units in color space, of the thing that I click. So now this should be better. So if I click on the ribbon again, I guess it's thinking. So here, this is the segmented image. And let me just put them side by side again. Right, so I clicked on something blue, and I came up with the blue box that says Marlene, the blue ribbons on the left and the right, the blue stickers on a couple of the bananas, right? So that seemed to work pretty well. If I was, again, this just with any thresholding, if I had made that distance bigger, I would have gotten more stuff that was closer to blue. If I made it smaller, I would have gotten less stuff. So let's try it on the banana. So, things don't always work the way that you expect in color space. You have to kind of think about, okay, so what colors are actually close to each other? So here, if I look at what I ended up with, I got the bananas mostly, although places where the bananas were darker, I didn't do a very good job. But I also picked up some things that, maybe some of the yellow peppers, and this box apparently here, like this light green, is close enough to that yellow in color space. I guess it's kind of like an unripe banana, right? So, you have to be careful about, what's going to work, right? And clearly, whenever I do any sort of thresholding, and this is going to be leading into what we talk about next time, you get lots of kind of extra crud, right? So for example, I would really like to be able to take these bananas and I would like to be able to fill in these blue seals on the bananas, right? Because I know that that's kind of part of the banana. Or I'd like to say, okay, I want to get rid of this crap in the background that is clearly not what I'm looking for because it's too small and too out of the way. So things like, how do I fill in holes? How do I get rid of extraneous crap? That kind of thing is applied, is called morphological image processing, and it's applied to try and help clean up some of these kinds of things that you see here. So we're going to talk about that next time. And the last thing I want to say is that, those of you that are taking kind of like a machine learning class, for example, one way I think about this in a more general sense is that, I've got pixels that are clustered together, or that are out here in RGB space, right? And so you might imagine that what I could try to do would be to try to apply some sort of a machine learning algorithm. For example, I could try to find a hyperplane that splits apart the clusters in the world as nicely as possible, right? This could kind of be like a generalization of Otsu's algorithm, except instead of finding a single threshold, I'm finding the parameters of this plane that's cut through RGB space. Or I could say, okay, I'm going to apply a clustering algorithm, like a k-means clustering algorithm, to try and find, clusters in space, and then I'm going to associate RGB points with their closest cluster, right? So those of you that are taking some sort of a pattern recognition class or machine learning class may be able to see ways to apply these kinds of algorithms to things like color segmentation, okay? Okay, so any questions or comments about thresholding? Good. All right, so